In this lecture, we talk about a lemma in which we describe the integral closure of an ideal of a ring. And so let us see this in detail. So say there is a ring A which is contained in ring B, and there is an ideal A which lies in this ring A. So an element B in this ring B, this is called integral over an ideal A if it satisfies the following monic polynomial. So same definition as being monic over ring A, but now the coefficients lie in ideal A. Now set of elements of B which are integral over this ideal A is called integral closure of this ideal A in B. So as before, we again say that an element small b in this ring capital B is integral over this ideal A if it satisfies the monic polynomial right here. So instead of x, we plug in b, and it should satisfy the monic polynomial. Again, the coefficients lie in the ideal A. Now if b to the power of p is integral over this ideal A, then so is b, because if b to the power of p is integral over ideal A, there is a monic polynomial which this satisfies. So we plug this in the monic polynomial, and the same will work for b with small changes, you can say. So same monic polynomial can be used for b. So if b to the power of p is integral over an ideal, then so is b. Now we come to the lemma we were talking about. So let a prime be the integral closure of a in b. Then the integral closure of this ideal a in b is radical of a prime. So again, this ideal A lies in here. So then you can construct its extension here in B. And we can say that there is an integral closure of this ideal A in B is precisely radical of this ideal in A prime. So we can consider an extension of this ideal A which lies in this ring A in A prime and take its radical, and that is the integral closure. So let us see this. So the first thing we are going to prove is, so you pick up an element in ring B which is integral over this ideal, then we will show it lies in the radical of A prime. So to show that it lies in the radical of A prime, we have to show some power of B lies in A prime. So you start with B over A prime. So since B lies in A prime, where A prime is integral closure, you have some equation like this. In fact, you have an equation like this because B is integral over A, and then B lies in A prime for sure. So this is precisely this equation. Each of the coefficients lies in A. So now we can write Bn as, take everything here on the right hand side. You have minus An minus 1, Bn minus 1. Then, so all of these elements now lie in A prime. So b to the power of n lies in A prime, and therefore we are done. So now we go in the opposite direction. We pick up some bm in the radical ideal, and then we have to show that this b is actually integral over the ideal A. So you pick bm in this radical ideal A prime. So if you pick up something like this, it has to have the form like this: summation ai xi, ai lies in our ideal and xi lies in A prime. That is precisely the definition of bm lying in A prime, something like this. And since xi lies in A prime, each of the xi is integral over A, because A prime itself is integral closure of A. So all elements of A prime are integral over A. So now we can construct a module M which is A x1 to xn. Now this is a finite A algebra. So if you put each of the elements integral, attach it to A, you will get a finite A algebra, and this follows from the proposition here which we have proven before. So let R be a ring, A a subring of R, and these xi's be a finite set of elements of R. If for all I, xi is integral over A x1 to xi minus 1, or in particular all the xi's are integral over A, which is our case, all the xi's are integral over A, then A x1 to xn is a module of finite type. And that's precisely what we are saying. The M is a finite A algebra, or A module of finite type. So if this is a module of finite type, then we have this case here. By definition, this Bm would be integral over A. So recall our definition. So the definition of being integral was, let R be a ring, A is a subring of R, and X an element of R. An element X of R is integral over A if it satisfies, this was the part C of our definition. There exists a subring B of R which contains A and X, which is an A module of finite type. So this B is an A module of finite type. So instead of B, we put in M. This contains A, and instead of X, it contains BM, because BM is a combination of this, and M is A x1 to xn, so obviously it contains BM. So, and this is a module of finite type. So then by this definition, BM would be integral over A. So notice we are talking about integral over an ideal, and here we have a ring. In fact, the same procedure which we showed here in C would carry over here, just because these definitions are similar for being a monic polynomial here and here. So nothing is lost if we say instead of A we replace with this ideal A. So this was the lemma which we wanted to prove. So let us now consider integral closure in field of fractions. So say E is an extension field of fractions K of normal integral domain A. So we have this normal integral domain A, so that is, it is its own integral closure in its field of fractions, and obviously it lies in K, and then you construct an extension of K which is E. Now if alpha in E is integral over this ideal A in A, so you take alpha in E, this is integral over some ideal A in A. So then the minimal polynomial associated with alpha, so this alpha lies in extension of K, so it has some minimal polynomial associated with it. So there is some minimal polynomial associated with it. So then the minimal polynomial associated with alpha has coefficients in K. So minimal polynomial which is associated with alpha will have coefficients in K. It is by definition of having a minimal polynomial associated with alpha in the field extension E over K. So this alpha corresponds to a minimal polynomial which has coefficients in K, just like in Galois theory. Now then these coefficients which actually lie in K would also lie in the radical of A. So they will actually come down to be in the radical of A. So the coefficients already lie in K, but they actually now, we are saying in this lemma that they actually lie in radical of A, which is obviously smaller than K. So let us see the proof of this. So say alpha over E is integral, so it satisfies a monic polynomial like this. You have x to the m, you have x to the m minus 1 coefficients, so plug in alpha m, satisfies this monic polynomial, and so this is integral over an ideal of A. So each of the coefficients lies in the ideal A, which in turn lies in the ring A. And corresponding to this alpha, there is a P which is associated minimal polynomial for alpha. So this minimal polynomial corresponding to alpha is P. Now we construct, so this minimal polynomial has coefficients in K. So now we construct this extension L of K. So now we construct an extension L of K, and this L contains all the roots of this polynomial. So L contains K and all roots of our polynomial P. Then within L we have an isomorphism K alpha to K alpha prime, where both alpha and alpha prime are roots. They are roots of polynomial and they are conjugate to each other. So they are just called conjugate to each other, the roots of the polynomial. And recall in Galois theory, how did we construct this isomorphism? So we had Kx over P. This was isomorphic to K alpha prime and also to K alpha, where alpha and alpha prime are both roots of our minimal polynomial. So where alpha prime is another root of P. Now you can apply an isomorphism here, because this you can consider it in K alpha. Obviously A further lies in K, so this entire thing lies in K alpha. From this field we can construct an isomorphism to K alpha prime, which does nothing, which maps K to K and alpha to alpha prime. So this entire equation here will become this equation in k alpha prime. So what we have done, we've done nothing. It is an isomorphism to k alpha, from k alpha to k alpha prime. So everything is constant except alpha is changed to alpha prime. That's what alpha is changed to alpha prime. Everything else the same. Now we have carried this equation to this equation, but now it shows that alpha prime is also integral because it is satisfying the same equation. So we have applied isomorphism to the monic polynomial here, and we get this. So this shows that all conjugates of alpha are integral. So all the roots of the minimal polynomial are actually integral. Now since the polynomial will split like this in our splitting field L, that shows that the coefficients of the polynomial, this coefficients of our minimal polynomial, they are made out of these roots. So after all, any coefficients you get after multiplying this out are combinations of these roots. So the combinations of roots gives you the coefficients of the polynomial. And therefore all the coefficients lie in the integral closure of this ideal A, because coefficients are made up of these roots of the polynomials, which we call conjugates of each other. All the roots are integral, and we know that all the integral elements form a subring, so their combinations are also integral. So therefore everything lies in the integral closure of this ideal A, because we are starting with this ideal A. And this ideal A is radical by this lemma. So let A prime be an integral closure of A in B. Then the integral closure of A in B is radical of A prime. But in our case, we are saying that we have a normal integral domain A. So A is equal to A prime. So A is equal to A prime. So this is just, we are saying radical of A. So integral closure of A is radical of A, because A prime is A, by this lemma we have proved before. So we can actually say something more or something similar to this. So let A be a normal integral domain with field of fractions k, precisely like this case. So k is the field of fractions of normal integral domain A, but now we are considering a finite field extension. So if you have a finite field extension, then you can, for corresponding to every element here, we have a minimal polynomial. So element alpha in E is integral over A if and only if minimal polynomial of alpha has coefficients in A. So obviously this direction is clear, because minimal polynomial by definition is monic. So you have a monic polynomial which is associated with alpha. That means alpha is actually the root of that minimal polynomial. That is what association means. So that minimal polynomial, which is a monic polynomial, satisfies alpha as a root, and therefore alpha is integral. So only thing we have to prove is in this direction. So in this direction, say alpha over E is integral, and say P is the minimal polynomial associated with alpha. So let L be the field containing K, just like in this case, and all the roots of our polynomial P. So L contains, say, alpha prime and alpha, again like this, both of which are roots of our minimal polynomial. In particular, we are saying that alpha is in E, it is integral over A, so it satisfies such an equation like this. So you can plug in alpha here, and alpha will satisfy this equation precisely like this. So here we had x to the m, here we have x to the n. This is just a different equation. Now again we can apply this isomorphism k alpha to k alpha prime. So if alpha satisfies this equation, then alpha prime will also satisfy this equation, just like here. Because you have this isomorphism, you can send alpha to alpha prime. So that means alpha prime also satisfies the monic polynomial which alpha satisfies. So again our polynomial in L will split like something like this. So the coefficients of the minimal polynomial are made out of sums and products of roots. So where each of these conjugates is integral over A. So where alpha, alpha prime, all the roots are integral over A. But A is integrally closed, and we know that these combinations are in form a ring integral over A, but A is integrally closed because A is a normal integral domain. So all the coefficients lie in A, and that's what we wanted to prove, that element alpha in E is integral over A if and only if the minimal polynomial of alpha has coefficients in A. So notice that in general, when we talk about minimal polynomial, we are talking about this alpha taken from this extension. So when you're taking alpha from this extension, its minimal polynomial will have coefficients in k. So what we are saying is, if you put the statement of being integral, this goes down further to this ring A, from which we constructed this field of fractions. So we had A lying in k. So minimal polynomial has coefficients here, but forcing it to be integral makes sure that these coefficients actually lie here.